Courses in the cement industry. Present to you. In this topic, it will be explained. Tire and roller reconditioning, grinding. As your kiln ages, tire and roller surfaces may show pitting, spalling, cracking, and other wear problems. The result: vibration, high power consumption, kiln alignment problems, and short bearing life. Worst case scenario: unplanned downtime and extended outages that impact your productivity. Resurfacing tires and support rollers helps you avoid these problems by improving mechanical stability and extending equipment life. Tire and roller grinding. Why resurface? Wear problems on your rotary kiln tires and roller surfaces are inevitable as your rotary kiln ages. But if they are allowed to continue, they will not only affect power consumption and operating costs, but can also lead to premature bearing failures, damage to tire retaining components, bases, drive components, and piers and footings. Resurfacing can correct issues such as 1. Concave and convex wear. 2. Rolled over edges. 3. Timing marks. 4. Taper wear. 5. Spalling. 6. Circumferential grooving. Tire and roller grinding. Why must tires and rollers be reconditioned? Because when tires and rollers are not smooth, they are not making even contact with each other. Wear patterns develop, accelerating wear, increasing cost of operation, and eventually causing component failure. Thermal expansion. To fully appreciate what is involved, the way thermal expansion is accommodated on this very large piece of mechanical equipment must be understood. Because its operating temperature may be considerable, careful planning for handling thermal expansion is necessary. Roller adjustment and skew. But thermal expansion is only one factor, which needs to be considered. Improper roller adjustment and skewing also cause wear to rollers and tires, and may hasten the need for reconditioning. Thermal expansion of the rotary kiln. This figure explains overall growth thermal expansion of the rotary kiln at 100 to 200 millimeters. We follow together thermal expansion of the rotary kiln. Axial and radial expansion. All trunnion or roller supported rotary equipment has axial movement of the shell. There are two causes for this movement. It may be thermal in origin, where an expanding shell continually repositions its tires on stationary rollers, or the movement may be caused by the normal play in every unit, refractory lined or not. A typical rotary kiln can grow 100 to 200 millimeters in length, axial expansion, from a shutdown, cold condition to its normal operating condition. Each unit will expand differently, since expansion depends on both size and temperature difference, cold to hot. A dryer or calciner which is not subjected to extremely high temperatures, may not have as large a variance. The diameter also grows. Radial expansion axially and radially gives designers of rotary equipment some special challenges. Of particular concern in this discussion is axial expansion. We follow together thermal expansion of the rotary kiln. This figure explains. The tire moves laterally on the roller. We follow together thermal expansion of the rotary kiln. Lateral movement. Each pair of support rollers carries considerable weight, which can vary from a few tons to as much as over 1,000 tons. With that much weight, even the smallest variations in the profiles of the rolling surfaces can have significant and detrimental effects on the entire unit. If the rolling surfaces are not flat and cylindrical, Any axial movement causes additional loads to be transmitted throughout the mechanism. The magnitude of these additional loads can be substantial and severe. These loads are transferred from the shell, which is the prime mover, through the tire retaining blocks to the tire, to the roller, to the bearings, to the structural base and finally into the foundation. All the parts in this mechanical chain act to absorb the additional load. We follow together, thermal expansion of the rotary kiln. This figure explains tire problems. See in this figure. 1. Stop block wear. 2. Cracking weld in shell. 3. Mushroomed edges causes tire cracking. 4. Poor contact to roller, equals higher and faster surface wear. Lead to refractory problems. We follow together, thermal expansion of the rotary kiln. Tire problems. When the load becomes excessive, that is beyond the carrying capability of the weakest component, rapid deterioration and ultimately component failure occurs. Worn side faces of the tires, worn stop blocks, and cracked welds will be visible. When the tire is prevented from moving freely, across the face of the roller even a few thousand, this of an inch of unevenness, can create enormous additional pressure on the tire. All of this pressure is absorbed by the unit, but the increased force requires the drive to exert additional effort. The shell is much harder to turn. The additional energy required by the drive translates to additional cost of electrical consumption. Unfortunately, the result does nothing but grind up metal. We follow together, thermal expansion of the rotary kiln. Roller problems. The chain of reaction does not stop with the tire. The additional loads created by the tire's inability to move freely in the axial direction are also transmitted to all the components of the unit. When the load becomes excessive, that is beyond the carrying capability of the weakest component, rapid deterioration and ultimately component failure will occur. Broken roller shafts, hot thrust bearings, cracked or distorted base frames, cracked grout, and even wobbling piers are the telltale symptoms. In worst-case scenarios. Resurfacing techniques. Techniques for in-place grinding. The first and crudest attempt is to place a cutting tool near the bottom of the tire. This may have a limited degree of success, but will leave the tire surface very rough, not necessarily cylindrical and often with steps in it. Sacrificing far more material, and hence tire life, than is necessary to restore the surface, in order to try to get minimal acceptable results is a big drawback. The belt grinder produces a beautiful finish, but unfortunately does little else. If cosmetic improvement is all that is required, this method is adequate. Usually a considerable amount of material needs to be removed from specific areas, the high spots, in order to flatten the surface. Belt grinding is somewhat indiscriminate as it removes material. Material removal is slow, and it is not just removed from the high spots. We follow together, resurfacing techniques. Techniques for in-place grinding. A cup grinding stone, whose cutting position is firmly indexed on a fixed arc, guided by the tire surface itself, is the technique whereby a flat surface and a true cylinder can be cut back onto the tire, even though it rotates without a true center. Of all the different methods that have been attempted over the years, see this video about grinding in situ.
When rotary kilns or dryers need maintenance, two primary concerns must be satisfied. First, the job should be guaranteed. This requires the experience of a company that understands the unique operating characteristics of roller-supported equipment and one that sets high-quality standards of workmanship. Kiln Surfaces pioneered an in-place grinding process that corrects the common wear problems on tire roller surfaces. The first problem, minor pitting and spalling, is one that can be easily overlooked. Foreign objects or abrasive material can cause small surface craters which initially don't appear very threatening. However, if they are left uncorrected, high-stress areas develop which can eventually cause tire and roller surfaces to crack. The second wear problem, tapered tires and rollers, occurs when rollers are misadjusted or skewed so their axis of rotation are no longer parallel to the kiln. As a result, the tire or roller diameter becomes slightly smaller on one side. The surface load is not properly distributed, and the tire tends to shift toward the side of the smaller roller diameter. This shift can result in premature bearing failure and put undue stress on the stop blocks and support pads, causing excessive wear and cracked welds. The third wear problem, convex and concave wear, is actually a result of normal roller adjustment. As rollers are adjusted to take thrust, the adjustments naturally put uneven pressure on the rolling faces, creating the convex and concave wear pattern. This pattern makes thrust control and roller adjustments increasingly difficult as the wear patterns deepen. Horizontal marks or flat spots on tires and rollers are a fourth common wear problem that can be corrected by in-place grinding. These marks are caused by excessive gear wear or roller or gear misalignment. Continued operation on horizontal marks and flat spots can cause vibrations, which usually result in damaged bearings, piers, and footings. When these common wear problems are detected, the grinding process can remove them. The first step involves carefully setting up the equipment. With proper machine setup, the accuracy of the machining and the safety of crew and plant personnel are assured. Grinding the tires and rollers can usually take place while the unit remains in normal operation with no downtime production loss. There are three key points to assure a successful grinding operation: the use of machines specifically designed for the purpose, utilization of proven procedures, and employing experienced personnel. The grinding machine uses a cup grinding stone, which produces a more efficient, more accurate machining job and results in a smooth surface finish. Experimentation with other machining methods, a cutting tool or a belt grinder, for example, produces poor results. They remove material indiscriminately and leave a rough cut that makes roller adjustments difficult, if not impossible. High and low spots are often apparent after using a cutting tool or belt grinder. The unique design of this machine senses the highs and lows or out-of-round spots on the tire surface. It then automatically adjusts to maintain the needed contact with the tire. As a result, the cup grinding stone takes a heavier cut along the high areas and a lighter cut in the low spots. With this design, an experienced operator can eliminate timing marks, out-of-round conditions, and highs and lows on tire surfaces. Specific procedures make this a reliable and predictable grinding process. The use of electronic devices to measure the circumference of the tire and roller surfaces without shutting the unit down guarantees that circumferential dimensions will show 10/1000ths or less taper across the face. If finer tolerances are required, the unit can be shut down briefly for a more accurate measurement to guarantee 5/1000ths or less taper. Written verification of these measurements is provided upon completion of the grinding work. Another important part of the grinding process is to work on the tires and rollers simultaneously using a specifically designed tire grinding machine and another machine designed for rollers. The removal of work-hardened surfaces leaves the tires and rollers susceptible to damage until they can work harden once again. Simultaneously grinding the tires and rollers gives the newly machined surfaces that opportunity to work harden without damage. Another benefit of simultaneous grinding is that roller adjustment is easier. Removing material to correct wear patterns can cause sudden kiln reactions. Since roller adjustments are required while grinding, smaller moves suffice because tires and rollers will have enhanced contact. Roller adjustment is a very important part of the grinding process. Adjustments to balance the kiln thrust before, during, and after the grinding work require experience and knowledge. We will share that experience and knowledge with you for your future use. Our supervisors have completed grinding jobs in more than 400 industrial plants and have a combined total of more than 75 years of experience with roller-supported equipment. The experience of the field crews is enhanced by an active research and development program. The grinding machines are constantly updated and improved by computer-aided design methods. At regular intervals, each grinding machine is overhauled and rebuilt to maintain design specifications. Your next kiln inspection should allow you to detect the presence of any of these common wear problems. A visit from one of our service engineers will assist in defining the extent of those problems. Use of the tire grinding process as a preventative maintenance tool will help establish predictable mechanical performance of your kiln, dryer, or other trunnion-supported equipment. Patented service equipment and methods, experienced personnel, and guaranteed results.
Thank you for watching, and I hope these courses are helpful to everyone. Subscribing to this channel Cement Industry Courses would be appreciated. Thank you.